welcome to this physics problem. This is a classic high school physics problem, and we have what we have here are two blocks, 5 and 10 kilograms. They're connected by a string which has been looped around this pulley. We're going to have to find the tension in the string and the acceleration of the blocks. Before we get started on the problem and how this works, first I want to notice two things, massless and ideal. If we imagine a rubber band, right, and we pull this in, here's what the rubber band normally looks like, but then we pull it, right, maybe there's a hook here, and we connect, and that's connected to the ceiling, and then right here we connect a block, and when we connect the block, it pulls down the rubber band and it stretches it out, like kind of to here. Well, now, because we have stretched down some slight amount, the rubber band, which resists the stretching, has these ends getting pulled back to the unstretched position. The ends of the rubber band, which are now stretched from this configuration, they've been stretched, they resist the stretch and they point back toward the middle. They act on the ends, and the ends are getting pulled back in. We've been saying all along that we imagine the tension is distributed evenly through the rubber band, and what we mean by that is that the tension at one end is equal to the tension at the other end. The word ideal gets us this fact. When we say ideal, we mean the tension at the two ends is equal. So now we see why the word ideal is there. What about the word massless? This word massless. Consider, oops, those arrows came out of nowhere. Consider, if you take a penny or like a nickel or anything else, and if you were to set it on the block, it has some mass, therefore it has weight, and its weight will push down on the block and exert an extra force on that block. And by the same logic, you might be thinking, this rope right here has some mass, and that mass is pressing down on the 10 kilogram block, so there should be another force of the weight, of the rope's weight, pushing on the block, right? And, you know, if you thought this, you might have a pretty good point, except, that's why we put massless in when we describe the rope, so that we avoid this whole issue altogether, the issue. Okay, let's get started. We've seen pulleys before, but not like this. Not like this. A pulley it's basically a wheel that can turn, it can rotate, and there's an indentation along this edge. So if you looked at the, this is your eye, right? If you were to look at the pulley, you would see an indentation, and that's where that indentation is where the rope lies. The wheel can turn, and in fact, when you connect two different blocks, one heavier than the other, then the wheel will turn as the blocks move. So which way are the blocks going to move? Are they going to move like this way or this way? Well, we see there's a 10 kilogram block that's heavier than the 5, so the 10 kilogram block pulls down harder, and that will cause the wheel to go this way. The 5 kilogram block will raise up, 10 will go down. As these blocks move, they do not move at a constant velocity. In fact, they are going to accelerate. As the 5 kilogram block goes up, it will speed up, and as the 10 kilogram block goes down, it's going to speed down. It's going to speed up as it goes down. That's what we mean by acceleration. The velocity is changing. Okay, first step in these problems. Draw the forces acting on the blocks. The one on the left is being pulled down by gravity. We are going to assume in all of these problems that gravity's acceleration is 10 meters per second squared. So we find the force of gravity using m times g. Mass is 5. G is 10. Multiplying those gives us 50 newtons. Force we measure in newtons, so we put 50 newtons. Right. A much bigger gravitational force is acting on this this block. So let me move my ground down a little bit. There we go. And twice that, so the arrow length should be twice as long. This one is being pulled with 100 newtons, 10 kilograms times 10 meters per second squared. Okay. In addition, this rope that goes around has been stretched because of these, stretched ever so slightly because of the masses hanging on the ends. So normally, this end comes to like right here maybe, but it's taut. That rope is taut, so it's been stretched down. Because of that stretching, this end is pulling up. The force in the rope we call tension. It's the force trying to return the rope's two ends back to their unstretched configuration. Okay. And then right here, this rope normally comes down only to maybe here or something, but we've stretched it down ever so slightly. And because of that stretch, it's being pulled back up. We know that this value of t equals that value because of our ideal string. Now, this is the picture. In fact, as we'll see, the tension is going to be less than 100. So this arrow should be a little shorter than this arrow. The tension is going to be less than 100. And because of that, the block is going to accelerate down, and this one on the left will accelerate up. Now that we've drawn our forces, that's step A. Step A is draw the forces on the two blocks. Step B is choose a sign convention. Here's what I mean. Normally we say up is down and left is right. Sorry, up is down. Oh my gosh, it's a long day. Normally we say up is positive and down is negative. Right, like that. So what if we say that here, in this case? Up is down, up is positive, down is negative. If we say that, then the acceleration of this block, as it accelerates down, because it's heavier, this block will have a negative acceleration. Negative acceleration. And this block, which is accelerating upward, would have a positive acceleration. Oh, that is not good. That is bad. The blocks are connected, so they should have the exact same acceleration. One acceleration for this, whatever this acceleration is, this block should have the exact same value because they are connected, so they accelerate at the same rate. So here's what we have to do to fix this. Here's how we fix this. Take the bigger block, 10 kilograms. Whichever way it's going to accelerate, make that your positive direction. The bigger block is going to accelerate down, so that will be our positive. This is a positive, not a t. And up for this block will be negative. And then when you come over to here, remember that this block is moving with the same acceleration. So whichever way it accelerates will be positive, so it's going up, it's going to accelerate up, so that'll be positive, making down the negative direction. So if you were to connect these arrows, you see that pointing this way is always positive, and pointing the other way, kind of counterclockwise, is always going to be the negative direction. So we sort of are thinking about positive and negative using clockwise and counterclockwise. Okay. That's how we think about it. Step B is done. Step C, apply Newton's second law to the two blocks. Okay. When we look at the 5 kilogram block, what do? We say, okay, the total force. There are two forces acting on the 5 kilogram block. There's the upward positive force T and the downward negative force of 50 newtons. those are the forces on the 5 kilogram block. So you plug in then the mass of that 5 kilogram block. So we put a 5 here. We can leave the acceleration as a. We don't know it yet. And I'm going to write this as t minus 50 equals 5a. We do the same thing for the other block. What are its forces? Add them up and plug them into the left side of the equation. The forces on this one are the positive downward 100 newtons, so 100 newtons, and then the negative upward tension, minus t. And of course, the two t values are equal because of our ideal rope. What's the mass of that second block? 10. And then a is the same acceleration for this block as for this one. We have now a system of two equations. We have one unknown, two unknowns, and the same ones here. Two unknowns, two equations, so you solve using whatever algebra you prefer. There are going to be several methods to get the answer. So whatever you want works for you. What I will do is I will isolate t in the first equation, then plug it in here. Right? That's my method. So t then would be 5a plus 50. And then I could come and I could plug this in. I can replace t in the second equation with this expression, 5a plus 50. And when I do that, I get 100 minus 5a plus 50 equals 10a. And then I have to distribute the negative. This is like adding negative 1. You have to distribute the negative, as we remember, to both things in the parentheses, distributive property. And we get 100 minus 5a minus 50 equals 10a. You group all of the a terms together, and this is what we get. The acceleration is 50 over 15. And what is that? 50 over 15. Oh, I should be able to do this in my head. 3.3 meters per second squared. Don't forget your units. Like that. Now I'm going to erase my work since I have limited space. Alright then. Now that we've solved for the acceleration, finding tension is really easy. You just take one of these two equations, plug in this value of a, and solve for t. So I'll take the top equation. Why not? The top one. So t, I rewrite it, t minus 50 equals 5. And in place of a, I will put the unrounded answer that I got. I add 50 to both sides. And what do I get? 66.6 repeating, or let's just call it 67 newtons. And that is how you solve for the two unknowns, tension and acceleration. These are our answers, and that concludes the video. Oh, did I say watch in HD? I hope you watched in HD.